master's school in combinatorics and around combinatorics. As you'll soon find out, this is somewhat of a family business. So I'm delighted to introduce to you the head of the Israel Institute of Advanced Studies, Professor Michal Lineal. You're allowed to guess what the relationship is. And please, Michal.
Boker Tov. Welcome. And let's see. Okay. So when Nati said it's a family business, it's deeper than you think. I'll take a few minutes to introduce to you the Institute. I'm sure that for some of you, it's a new place that you are here. How many of you have never been in this room? Wow. Wow. How many of you have never been in Israel before? Unbelievable. We should take a picture of this. Maybe we'll do a simulation later, but that's very impressive because one of the reasons of making this midrasha, or as we call it, advanced school, is really to do what you just showed us, that you are coming to this place, many of you for the first time, and clearly first time, or some of you first time in Israel, but I'm sure that, and I have to guess that in 2 weeks, these 2 weeks will not be forgotten for life. So that's quite important, and definitely it's not depend on me, as you'll see in a minute. So few words about of opening, of greeting. So it's really a great pleasure and honor to open this school, this midrasha. We are doing so many events, but as you can imagine, I have a special place in my heart for this one specifically. And one of the things that I always do when opening any, school or event or conference is that I promise to myself over more than 2 years by now that whenever we have something like this, I learn something about the topic, and at least I'll sit in 1 or 2 lectures, and usually I grab the organizer and say, okay, choose one that I can sit and learn something. So first of all, when I did it, the answer was there are only 46 that you have to sit in, or something like that. So everything is important. Everything is so you cannot choose one. Okay, so that was a bit of a hard start, but as you know, I mean, the many topics that we are doing here, that the conference and events runs from quantum informatics to a great meeting that we had on autism and mobilization of Mongol Empire and biblical literature and a script of magic knowledge and the Crusades and so on and so forth. Last a week ago, we just finished another school on 100 years for general relativity in theoretical physics. So my mind is a little bit spined by all those events, but let me say why this school is so unique and important. First of all, because, well, it's a personal business, and this poster was done by our daughter, actually. So this was done a year ago when the idea was just came in place. And I should say that I'm a biologist. I'm a biologist and computational biologist, and I know very well the combinatorics community over probably 40 years of my life. And actually, this unique case, I know all the organizers, most of them 35 years. Those that I don't know 35 years just means that they are younger, that's all. But otherwise, I know them all. And I just wanted to tell you that combinatorics in and around, I was thinking about it, and I realized that in and about combinatorics is something that I live with for the last, as I said, 40 years or so. And let me tell you that it's not me that I live around it, but actually the biological community. And just for curiosity, I show you 10 papers, just a random selection of 10 papers from biology, in which the word combinatorics in the title from the last 5 years or so. And just for you to see how much it is in and around, I can show you that it's about RNA structure, about high-dimensional space using ribosomes, about RNA structure again, and some inference, some bridge mechanism. This is pain processing, on pain, on neurite self-avoidance, on RNA interaction and probability. 10 years on predicting whether a relation will occur, about relation, and about therapy. And this is just a random selection. So it's a good sign to say that you are not that isolated as you may have thought maybe many years ago. And actually, I can say something personal. If you cannot beat them, maybe join them. And this is our papers. I mean, for last few years, as you can see, my paper and with my team, combinatorial regulation, combinatorial nature, combinatorial analysis, and so forth and so on. I'm here for the coming 2 weeks, so you can ask me what type of combinatorics is it. So the one thing that are very important is really the enthusiasm, I think, that I was witnessed for many years about open problems, about posing new problems, not always about solving them, but about really putting on the stage for the community the right problems. And in this school, I think what you are doing is trying to find hidden connections. And what can we provide to you? We can provide to you the right setting, and you can see that you can guess what they are doing here. Those are two of your organizer speakers. We provide you 2 big boards, and I must tell you, this is the midrasha number 18. 17 midrashot before you, everything was fine. But now they said, okay, if we really want to do mathematics, really wants to do it for 14 days, really wants to do it that everybody can learn and enjoy, and we need new boards. Okay, so we have new boards for you. But this is not enough, because we need also very good coffee, because this is all about mathematics. You put in coffee, you come out with some lemma, some conjecture, or something, right? So we will provide good coffee, I hope. But we also provide many yellow pads. As you can see the coloring, but you can imagine that this table is packed with yellow pads, and you can start doing this. And fortunately, you have really serious organizers. And if you can offer, can you shut down the lights a bit? And this is Gil trying to beat gravity, trying to show that he can walk on the campus with a pine cone on his head. And this is, just a routine day. It's not like a special one. Sorry. Oh, okay. And what we can't provide you is equipment to solve problems. So if you have problems, you just do it. And sorry, no skis, but still can do it. And just to say that we do not, as I said, provide equipment for solving problems. This is Nati and Gil trying to get out of their suit with no success, as you can see on the face here. And so I think by that I can just say, enjoy the school and have a great 2 weeks. And welcome to Jerusalem, welcome to Israel, and to the Midrasha.
Hi. Before I pass the floor to Irit, the first speaker, let me take 2 minutes and suggest to you just how to organize your efforts in this school. It's going to be 2 very intense weeks. And since I presumably thought about this in the month before this more than other people, let me suggest to you just how to organize your efforts. It's going to be very intense. Of course, it will be wonderful if everyone went to all the lectures and studied everything in great detail. Presumably, it's going to be too much to expect of yourself to do all of this. Don't let this discourage you. We have, I'll say a word about this. We have 7 series of mini courses, you can say, 7 series of lectures, which I'll say a word about in a minute. And in addition, some individual lectures on various subjects. The two things that I'd like to suggest to you when you plan how you're going to approach this is set yourself realistic realistic goals. So of these 7 series, select for yourself a number that are more interesting, closer to you, and so on, which you may want to study intensely. And I hope there will be some homework assignments or problems you can think about. Others, it's okay to just come and try to expose yourself to new ideas in a more shallow way, and that's perfectly fine. And the other more encouraging part of this is, I think most of you already know, that just by sitting in on lectures that perhaps initially you don't understand everything, all of a sudden you start seeing that you understand things. So don't let subjects which are a little bit out of your circle of backgrounds discourage you. Let me just say just very few things about this series of lectures. So just to set ideas, we have 2 series of lectures by Kivash and Samoti, which you can say are in the core pure combinatorics, all sorts of really wonderful discoveries of the last few years. There are 2 series of lectures on connections between combinatorics and theoretical computer science by Dinur and Steurer. There is a series of lectures connecting combinatorics and free probability by Nika. A series of lectures by Haas on topology, and a series of lectures by Postnikov connecting combinatorics and algebra and geometry. And as I said, in addition, there are individual lectures. So look at the material, construct for yourself your own schedule, the lectures that you're going to attend very seriously and take notes and think about and so on, and those in which you sit and just get an impression of the field. So just 2 last small comments. You may have seen, but I'm not sure that you have noticed, there are these desks downstairs. They're not there just to put your coffee cups on. They're actually showing work, original handwritten, I mean it's facsimiles, but still of the original handwritten papers and correspondences by Albert Einstein, and the Hebrew University is where all his remaining letters and handwritten things are kept. So you may find those interesting. There are remains of the meeting that Michal mentioned of 100 years of general relativity. And the other thing that I was asked by the office is we have several social events here. And please take the time and do it today. Register to those that you're interested in, because they really need to have exact numbers and exact names so they can get them started. And unless there are any questions or comments, okay, so I'm happy to introduce Irit Dinur, who will start her series of lectures. Irit. עופר, אפשר להרים את המסך?
נתי, אתה רוצה להגיד על זה שיהיו וידאוים של ההרצאות, שאם אתה מפספס הרצאה...
אוקיי. Yeah, okay. Irit told me. We hope that without any failure, we're going to record all the lectures. And if everything works according to schedule, which I hope it will, about 15 minutes after the lecture ends, it will already be online. So if for this or that reason you've missed a lecture, don't despair. You'll be able to see it immediately after, and you don't have to miss on any of the material. Okay, one more good comment. If you go online and you look at where the program is and you click on the name of a lecture, that will immediately give you the recording. So it will connect you immediately to the recorded lecture. So please, Irit.
Okay, thank you very much. It's so great to see so many people came. All right, so the topic of this lecture is direct products of graphs and games. And I'm talking today and then next week on Sunday and Tuesday. So my plan is today to give a lot of little tastes from little various things. And then next week I'll go deeper into 2 specific questions. All right, so let me begin. I guess I can start like this. All right. So, direct products in theoretical computer science are very useful for hardness simplification. So, as you know, or as you may know, in complexity, one of the grand challenges is to prove that things are hard. Because to prove that some problem is easy, you can find an algorithm, prove that it works. To prove that something is hard turns out to be much more difficult. We have much fewer tools for that, and it's something that we're more, we feel much more limited in doing. But one thing that we are very successful in doing is kind of reductions, to show that if some problem A is a little bit hard, then problem B is more hard. That's called hardness simplification. And one of the most general ways to achieve hardness simplification is through taking direct products. So this is kind of the core reason that I'm very interested in this. And as I'll try to show you, when you try to study direct products, you encounter a lot of interesting combinatorics. Okay, so direct products can be of various objects. So product is just multiplication. So just like you can multiply 2 numbers, you can also try to multiply other objects. So, for example, you can multiply functions. And if the functions are over a finite domain, and to a finite domain, then they're equivalent to just strings. I really apologize for this. So this is one object we will look at, direct products of strings or functions. Another is direct products of graphs. And the final thing that I'll talk about is direct products of games and what we call CSPs. CSPs are constraint satisfaction problems, you know, like 3-SAT or this kind of problems. So these are the objects that I want to talk about taking direct products. And let me start with direct product of strings. So if I have some string, you know, 0, 1, 1, 0, 1, like this, and I take some other string, then I can write the multiplication table, basically saying, you know, okay, so, and so on. Basically saying in each entry of this is going to be the product of the 2 string. I need to say how I combine these 2 elements. So the simplest way that doesn't lose any information is just to copy. So I will do concatenation. I'll copy the 0 from here and copy the 0 from here. So it will be 0, 1. This is in this item, 0, 1, 0, 0, and so on. In general, the product of these 2 strings, according to this specific definition, is a string that in location ij equals, you know, if I call this string f, equals fi concatenated with fj. Okay, so this. This one is perhaps G, but let me even talk about, you're right. So in general, this could be F times G, and then I would have, let me call this G. I would have Fi times, thank you, Nati, by the way, for, please do interrupt me. This is a summer or a winter school, actually. It's not a lecture in the sense that you should really understand and interrupt. Okay, so fi times gj. But kind of it would be convenient for me to actually multiply the same string with itself, in which case it will be fi times fj. Okay, so this is this new string has, if I'm multiplying f times f and f has some n bits, then the new string has length n squared. And of course I can write it out as an n squared long string, but it's also, as you see, convenient to view it as a table. Okay? And I can also multiply a string with itself more than once, so I can do f times f times f k times, in which case the result will be like a k-dimensional tensor. And in the, okay, so let me write it actually. Like this. Okay, so I will have f to the k is a n to the k long string. So here I'm assuming, of course, that f is some string of length n. Okay, so this is a n-bit string, or a function from the indices to the bits. And f to the k is going to be a string of this length, where f at location I1 up to ik is simply f at I1 concatenated with f at I2, f at ik. All right, so this seems like a kind of trivial definition, but one kind of interesting way to think about it is that if you have a string, this is my f, my original f, then what does f to the k provide to me? It provides me with local views of this f. So for every k tuple of indices, say I view this k tuple as kind of a window, and fk tells me the value of f in this window. Okay, so fk, let me call it capital F, is a function from n to the k to 0, 1 to the k. And what it tells me is that, in this, so actually let me denote it here. In this k tuple of indices, the value of little f is something. Okay. Now, when you do hardness simplification, the situation often is that you're given this object, and you try to understand whether or not it is really a true direct product in the sense that it really came from some original little f. Okay, so let's think about this question for a minute. We are given a collection of local views. Okay, so for every k tuple of indices, we are given some little string. And now we want to know, are these local views consistent? Is there really some underlying string such that all these local views are consistent with this underlying string? Okay, so the way I want to phrase this is that given the function f, as here, is it a true direct product? Okay, so either it is or it isn't. And if you are willing to go and check f on every single input, then it's very easy to decide that. Right? But the kind of questions that I will be interested in don't allow you to look at this f at every single location. Rather, you want to understand whether this kind of question is locally, you can decide it locally and in a robust way. So what does it mean locally? Locally means maybe you're only allowed to query capital F in a few locations. So you look at this local window and at this local window and maybe a few more. And you want to decide whether or not the capital F really is consistent with some underlying little f. And this is a question of property testing. In property testing, you look at some big object and you're only allowed to query it in a few locations randomly. And based on that, you need to decide, does the object have the property or not? So the question that I'm now interested in is the property of being a direct product locally testable. So I realize I haven't defined property testing. So I want to kind of explain it concretely on this question rather than define it in generality. So let me give you, let me suggest to you kind of a test for deciding if a given function is a direct product. So what can I do? What am I allowed to do is to query this object. So I'm given this function, and I'm allowed to ask for the value of f at certain inputs. Okay, so I'll choose some random input, some random k-tuple. Graphically, it looks like I'm choosing a random window. And f gives me an answer, a string of zeros and ones. And then maybe I choose sorry, another window. So it might be good for me to choose two windows that have some intersection between them. And I know already that the answer that f gives me should obey some kind of constraint. The constraint is that, you know, if it did come from a direct product, then whenever these windows intersect, the values here should match, right? So this is my suggested test. Choose a random window, I1 up to ik. Okay, and then choose a random window j1 up to jk such that maybe, you know, maybe t of these indices agree. So there is some the set I1 up to ik intersects the set j1 up to jk I don't know, in exactly t locations. Okay, and you know, maybe it's even better to think of these as multisets. Okay, so that if an index occurs here twice, then it's counted twice. Okay, so this is my test. And now the question, now, you know, here are some easy facts that I can show. The first thing is that if f equals f to the k for some f, then, sorry, I just says what to choose. I didn't say how to decide if to accept or to reject. So a test needs to test something. Okay, so accept if f at I1 up to ik, and let me denote this. Okay, so we have to introduce some notation. So let me, for now, just write what's the best way to do it? I guess let me just call this intersection set A, and let me denote it like this. So the way we think of it is, you know, we can think of f at I1 up to ik as a function from, you know, 1 through k that gives 0 or 1. And then A, if A is a subset of I1 to ik, then it's just a restriction. Okay, so I want to check whether f at A here equals f at A here. So, in other words, you know, it's exactly as the picture shows. You want to check that all the answers on the intersecting elements are the same. Okay. Yeah. All right. So there's at least two variants on this. One is that the function is from k tuples n to the k, and the other is that the function is from k subsets where the indices are not ordered. The way I wrote it right now, these are k tuples. So, you know, they're not. Yeah. So they're ordered, but here I put them in a set just to indicate that I'm interested in all the indices that occur many times. Okay. So what is easy to show? If the function is a direct product, then of course I always accept. Then the test, I accept with probability 1. Right? So I mean, this is kind of trivial. And then, you know, the contrapositive, the flip of this is that if the function is not a direct product, then there will be at least one query which will cause the test to reject. So this is, let's think of it as an exercise. If f is not a direct product, meaning there is no, what does it mean not to be a direct product? There is no function f such that capital F equals f to the k. Then the probability of acceptance of the test, so the test chooses a random and so on, will be less than 1. Then the test will not, but this is a very weak statement. It just says it will not always accept. It really doesn't talk about probability at all. It's just, does it always accept or does it not always accept?
What is the role of T again?
Great question. Yeah, so I was hoping someone will ask this. So there is this T here that I just put it out here. So, okay, so there is, so far 3 parameters. There is n, the length of the string. We think of it as going to infinity. There is k. Okay, it might be large, but it's some parameter. And then t. T obviously is between 0 and k. And it has a role. So for now, if you want to think concretely, think of some t equals k over 2. But really, t can be many things. It can be much smaller than k over 2. You can think of t being 1. So of course, t0 is not meaningful. So this actually, second item is not true if t is 0, right? Because then your test is empty, you will always accept. But the minute t is not 0, then the second item is correct. Okay. So now, an interesting question about this test, and so far it looks so simple, is that, you know, we want to understand how robust is this test. So we're looking at just 2 inputs into the function f, just f at j and f at I. And we want to know if f is not a direct product, you know, how often does the test reject? And in proper testing, we always try to kind of fit 2 things. The distance of the object from the property, so how far is capital F from a direct product, versus how often does this test reject. Okay, so these are the 2 things we want to match to each other. And okay.
An obvious question would be which choice of T is the most efficient, right?
Right?
With which T are you most likely to catch?
Yeah. So any guesses about that? So which T would you use if you want to test that a function is close to a direct product? Which T would be good to use? You know what? Before we think about this question, let me give you some kind of motivation that might help you to think about it. Okay? So one way to think of this question is that, you know, there is this big world of knowledge, right? And a lot of pieces of information. So every, you know, vertex here has some bit of information attached to it. And then, you know, different people know different subsets of the world. Okay, so I know this, and I know the value of these bits, and Nati knows, you know, this. And, you know, so each one of us, I should have been. Okay, so each one of us knows a little bit, and you know, and you know, are these pieces of knowledge even consistent? Is there really some global view of the world that's consistent with all of our local knowledge? You know, of course, some of our knowledge is wrong, right? I think I know, but it's not necessarily true. So sometimes I talk with Nati, and then it's, okay, so I need to change my bit. So it's really not what I thought. Right? So, okay, so, you know, this is kind of a reasonable model of how things are. You go, you talk to people, you update your data, and so on. And you want to understand in what situations does this kind of bunch of local views correspond to some one global view. Okay, so this is really the direct product question. You have a bunch of local views. These are the local windows. Okay, in my model, all of the windows have size k. And you want to understand under what local consistency conditions. So this is a local consistency conditions. This is really, Irit and Nati talking and trying to reach an agreement on the intersection of the bits that they care about together. So, so imagine, this whole, this evening in the reception we can play this game, right? So each one of us will go with a little window and with a collection of bits, and maybe they are not consistent in the beginning, and we mingle with each other and we try to flip our bits so that they become more and more consistent. And of course, I have nothing to talk about with someone who is talking about a completely disjoint set of bits. I only need to interact with people who, care about the things I care about. And hopefully, at some point in this interaction, this will converge, and we will say, okay, now we can lift all of our local views to some global, global function. This global function is my little f, right? So capital F is the bunch of local views, and the point is that there is some global little f whose restrictions are what capital F is talking about. So now you can ask, okay, so, in this imaginary game we will play in the reception, who should I be talking to? What size of intersection is enough for me to waste my time talking to this other person, right? And so on. So, so this is what is a good value for t, and by good I mean i.e. that will allow, so I'll use this, this word lifting the local solutions to a global solution, the local views to a global view, to a global f. Okay, so what I mean exactly is, if you want to be concrete, kind of mathematical, then I want to prove a number 3 here. So number 2 I said was kind of trivial. What I want to prove is a number 3. Number 3 says, look, if you mingle and you talk, and with probability 1 minus epsilon, 2 local views agree, then it means that there is a function little f that's, epsilon prime close to capital F. Okay, so this is a robust version of this. I said, if f is exactly equal to restrictions to local views, the test will always accept. If f is not of that form, the test will not always accept. But I want to know, what is the relation? What does it mean that f is not a direct product? What if you took a direct product function and you just change it on one location? Okay, so maybe the guys talking to this person will reject. Okay, what if you changed it on 1/3 of the locations? Maybe you change it so much that somehow it can fool you, and the test will accept very, very often, even though it's very far from a direct product. Okay, so we want to kind of relate these two things, and the kind of theorem we want to prove is that if the test accepts, I won't have enough room, right? With probability 1 minus epsilon, then f is close up to 1 minus epsilon prime. Okay, I'm writing short because I want it to stay in this board. To f to the k for some f. Question? No? Okay. All right, so you understand this is kind of a robust version of this. And, I'm not going to talk about this anymore today. I'll talk about it next week. Often when I gave this kind of talk, people would say, this is probably very easy to prove. And you'd be surprised, it's not easy to prove. And so I urge you as an exercise to try to think of it. So So try to think of it as an exercise, kind of a thinking exercise. What happens? Okay, so actually let me say a couple of more things. Okay, let's see what time it is. I have half an hour. Yeah, so I wrote 1 minus epsilon prime. The test acceptable probability 1 minus epsilon. You want to say that the function is very close, up to a distance of epsilon prime to a direct product. Does that make sense? That, this. As far as I know, right? It's correct. Yeah. Yeah. Okay, yeah. So that you're reading my mind. Great. So Eran is saying, for what t's can you even prove it, and so on. So before I say the exercise, actually, let's do it together. So, let's think about what t's are going on here. So, what happens for t that is equal, like, I don't know, k minus 1 or something. Okay? So, you really only talk to people that are very similar to you. Okay? So, will the test work? So I want to claim that it won't work. That the dependence between this epsilon and that epsilon will also depend on k. So whenever we have dependence on k or on n, then we're not happy. We feel that the property is robust when the epsilons are only dependent maybe on epsilon prime will depend on epsilon, but not on the other parameters of the system like n or k. Okay, so you know what? Actually, now I realize I only have half an hour. So. I go to 11. Oh, good. Okay, I was worried about this. Okay, good. So
just to mention, so now you're telling us that choosing it to be k minus 1 is a bad choice.
It's a bad choice. Okay. Right. So I want to. Does anyone have an idea why would this be a bad choice? K. All right. Yeah. Let's start with that. So t equals k. Actually, that's good for intuition, right? T equals k is a very bad choice because you only talk to yourself, right? So you're very consistent, everything is perfect, but you have no way of detecting inconsistencies. So, even this even fails, right? But, okay, so. That's true. So at least you will make sure that all the permutations are consistent. That's true. I didn't say it as a joke. I mean, even restricting to that, it's interesting to understand which permutations will kind of mix faster than other. Like, okay, never mind. All right. So for k minus 1, I'm claiming it's similar to this situation. It's almost like you're talking to yourself. You never get out of your village. Right, so you keep talking to people that are very similar to you, and by the time you get to somewhere else, so many steps have occurred, so that if there is even a large distance between your function and a direct product, this kind of talking to your village, you won't detect it. Okay, so let's see a concrete example. Think of having functions h1, h2, up to hn, different. Randomly chosen different strings. So each one of these is a string in 0, 1 to the n. Okay, or in my previous notation, hi is a function from n to 0, 1. Okay, and now think of defining f as follows. Let's have f at I1 up to ik equal hi1. So I'm using I1 to select which of these functions I'm using, and then I'm using the direct product on this h. So it's hi1 of I1, hi1 of I2. So I1 is going to stay the same up to h of I1 at ik. Okay, so now I gave you a definition of a function capital F. And I'm making two claims about this. The first claim is that capital F is far from being a direct product. Just because, for different values of I1, it's a direct product. but of a completely different function. So there's not going to be one single h such that f is simultaneously close to h to the k. Okay, so it's easy to see that f is far from a direct product. And now I need to ask myself, how often will this f pass the test, right? And so, if I agree on k minus 1 indices, the probability that I disagree on the first index is just 1 in k. So with probability 1 minus 1 in k, f at the locations I1 to ik and f at the locations j1 to jk, these are the two questions that my test is doing. With probability 1 minus 1 over k, I1 will equal j1, and then this test will pass. So the second thing is that f passes with probability 1 minus 1 over k. Okay, so if I think of as epsilon as a constant independent of k, then it passes with probability very close to 1, and yet it's very far from direct product. This test fails.
Okay, pass when what is the event that make it pass?
That I1 equals, so the test is this. Choose I1 to ik, choose j1 to jk, and test the function in these two locations. So if I1 equals j1, okay, of course these choices are not independent. They need to intersect on t locations. And in our case, t was k minus 1. So it means out of these indices, you choose one and you flip it, and this is how you get j1 up to jk. Okay, so this is the test. Okay, what's the probability that f will pass the test? Well, as long as you didn't flip I1, then both of these sides are talking about the same h of I1, right? So they will pass. Does this make sense? Doesn't make sense, okay?
It's about a half of it, no? Isn't it? You change, let's say, the earth coordinate. The i's, the
Yes.
j's are the same, except the I coordinate.
Has flipped.
JR is not.
JR is not equal to IR, but is J1 equal to I1?
No. I'm with you on this.
Okay,
Okay, so.
so you should have said yes if you were with me.
No. My students know when I say no.
You mean yes.
This means yes.
If it's a prime number of times.
Exactly. So you change the earth coordinate.
The earth coordinate. Okay, so now what am I checking? I'm checking that on the intersection. It's, I'm always checking only on the things that should equal. If you change something, I don't care about your opinion about things that I don't care about. So I only check on the intersection. So, if I change the earth coordinate, I check only on the all but the earth coordinate, and they are imperfectly equal. However, if I change the first coordinate, then even though I'm not asking about the first coordinate, the values on all the other coordinates here depend on h I1, and here they depend on h j1. These are two, I chose each of the h's randomly and independently. So these are two random functions. They disagree on half their location. So with very high probability, they will disagree.
So one more point. You didn't define for us how we define far. You're not.
Yes, I didn't.
But not,
Right. So, okay. Far. So you know how you sometimes say, okay, by example. So in this example, f of, when you have I1 and J, there is no definition of far under which this won't fall. This is far, okay? However, right, so I chose them randomly. Sometimes random events don't align in my favor. Agreed. Yeah, but Nati is right, and kind of, this research direction has been evolving for some time, and at first this theorem was proven under a weaker definition of far, and now we know how to prove it under a stronger definition of far. So what is the definition of far? Well, one thing you can say is, look, I look at the f, and I look at the closest function f. Okay, what does it mean closest? I look at the function f to the k, and I look at my given function f, and I look at every k tuple. Are they equal or are they not? And I count how many times they're equal. Okay, that's the strong definition of for the best function little f. A slightly more relaxed notion would say, you know, maybe little f to the k at a specific point does not equal capital F, but, you know, it's a k-bit string. Maybe it's equal on 90%. Let's count it as being near. Okay, it's like two people that are talking. They don't perfectly agree, but they mostly agree. Okay, let's pretend they agree. So for this relaxed notion, it's easier to prove the theorem. Okay, so it's another parameter, and it goes in with a t. But okay, let's. Okay, so let me finish with this part of the talk. I hope I convinced you that also for k minus 1, the test kind of fails. So for k, another thing to think about is what happens for t equals 1. What's going on here? And then, you know, the two interesting values of t are, one is like k over 2 or some, sorry, constant fraction of t. And the other is some, you know, like square root of k, or maybe even a smaller function of k. So there is some intersection, but there's a lot of randomness. You know, this is like, as I said, here you're only talking to yourself. Here you're only talking to people in your family. Here you're kind of randomizing only half of you're a little bit extending yourself. This is more expanding, right? So if you take a random walk on this graph of k tuples, then you can see that the smaller t is kind of the more mixing this random walk is going to be. And this makes the theorem easier to prove. Okay, I had some questions.
So do you know what the best is?
Yeah, so as long as you can prove it for this t, then it's the best. So this is the best t, but we don't know the exact trade-off between the value of t and like how, you know, what is the dependence between epsilon and epsilon prime. And there's still even easier questions we don't know. So
if t is 0 also, you cannot say that.
Yes. If t is 0, t is 0 and t is k is the same trivial thing. You're not testing anything. So yeah. Because when t is 0, you usually see two independent windows. You can't reject. You need to. When t is 1, yeah, so it's like you just choosing a specific bit you care about, and you check two people that look into that bit. So it's more like, yeah, so you can say something but very weak. It's kind of a trivial, it's not really a product. But yeah, okay. I'll move on. All right, so. Oh, yeah, I have no idea about that. I have no idea. Yeah. As I told Gil, there are even simpler things that I don't know. It does. So for the strong notion of far, meaning they must agree exactly, then you must have t to be linear. Okay? If you allow this kind of t, then you can see that you can't detect a function that's a perfect direct product and then every local window one bit was perturbed. You won't be able to detect it. So this kind of t, it's easier to prove because the graph mixes better, but it will only talk about a weaker notion. So yeah, there is some richness here to the structure.
So in particular for these two different notions of proximity, it seems like different t's would work better. So
yes, right. Yes. Okay, so let me just say one kind of question that is worth thinking about is what happens when you know that the test, think of some fixed t. Okay, so you're checking intersection on t bits. So now, you know, a random collection of local windows, if the test looks at t bits, the success is 2 to the minus t, trivially. So what if you know that the success is slightly bigger than that? Okay, so it's like 0.9999 to the power t. Okay, then does that imply some kind of structure on the function? This is a kind of question we care about and know part of the answer to that. Okay, so now I want to move from strings to graphs. Okay, so okay, now I realize before I erase, you know, okay, let me try it again without the bits. So I had these two strings, and I combined, and I defined the product by saying, look, I'm going to copy the 0 here and the 1 here and put 0, 1 in this bit. So it's like a local window. A more natural way that we usually do is that you take some kind of combiner function so that you have a bit here and a bit here, and you end up with a bit here. Okay, like the tensor product, right? So then you would take the product of the value here, or the XOR in this case, the XOR of this value with this value, and put it here. Okay, so when you talk about direct products, in my context, it's like you keep all the information. You copy this information and you copy that information and you keep it. In a direct sum, you compress the information and you start with a string. So in each coordinate the value is 0 or 1. And you want to end up with a string where the value in each coordinate is 0 or 1, not 0, 1 to the k. Okay, so then you would take the values here and you XOR them together. Why do I say that this is like this is a tensor? Because if these were plus minus 1s vectors, then it's just the outer product of this vector with this vector. It's just a tensor. And if you have in general a function from n to plus minus 1, then the tensor product f to the k, it takes a bunch of plus minus 1s in the locations I1 up to ik, and it multiplies them together. So it's like XORing these bits. So this is a related notion, direct sum of strings, and next week we'll probably talk about that as well. So this question is similar to the question of asking, if you're given a k-dimensional tensor, is it close to having rank 1? Rank 1 meaning, it's just some function raised to the k. Rank 1 means the product of f times g times h k times, but all right. Okay, now moving to graphs. So if you're given a graph, G1, V1, E1, and you have G2, V2, E2, then there's also a way to define the graph product. So how would you define the graph product? So as we know, there are several ways, and let's talk about that for a minute. So always the vertex set of G1 times G2 will be the Cartesian product of V1, V2. That's kind of very natural. So for every pair of vertices, you will now have a vertex. And now the question is, what is going to be the edge set? Under what condition are you going to connect two vertices? So we put V1, V2, and then we connect them to U1, U2. When? Okay, so there are a few definitions. Definitions are always like this. Look at the relation between V1 and U1, and look at the relation between V2 and U2, and then apply some kind of combiner function, like a Boolean function, to tell you if this pair of relations will be an edge. So for example, in one graph product, which corresponds to tensor, you put an edge if and only if V1 is an edge with U1, with U1 in G1, and V2 is an edge with U2 in G2. Okay, so that's one definition, right? So you see there's a Boolean function here. You check if this is an edge, you check if this is an edge, you get two bits of information, and then you apply the AND function. Okay, and then you get a decision when these two pairs of vertices. Of course, you could apply the XOR function. Okay, maybe it doesn't make that much sense, but you could do it. And if you have like k, the product of k different graphs, you really could apply any Boolean function. Okay, so there's one more information that you could use, which I didn't use. So far I just said for every coordinate, are these two an edge or not? Okay, if this is an edge and this is an edge, I will put an edge in my definition. But there is another graph product called the Shannon graph product that uses another piece of information, which is, do these two have an edge? And also, are these two equal. It could be that V1 just equals U1. Okay, so this is another kind of generic piece of information that we can have on our vertices. Right, so I mean, I have no idea what G1 and G2 are. I'm going to define my product generically. So what kind of relations do I have generically? So I have the graph relation. V1 has an edge with U1, and I also have the identity relation. V1 is equal to U1. So in the Shannon graph product, instead of doing this, let me call it this, I do the Shannon. It's if V1 has an edge with U1 and or V1 equals U1, and the same here, but except that okay, let me write it, and V2 has an edge with U2 or V2 equals U2, but I'm not putting self loops, so I should, but no new self loops. So unless there was a self loop before. No. Okay, so when am I allowing an edge here? At least on one of the coordinates I should be using an edge from the graph, and on the other coordinates I can either use an edge or use an identity. This is another kind of Boolean combiner function. Okay, and it turns out, so why do people even care about these things? Right? So it's kind of simple operations on a graph, and it's very.
So in the second definition, if I take product of x times, I might get a complete graph for the format.
Second? In the second definition.
If I take product of x with itself, I will get complete graph in 4 vertices. Am I?
You will get complete graph and 4 vertices. Yes, so people are quicker than me. Yes. Okay. Right.
There's a systematic way of listing all the different products. That's the only information that you need to do. That's the product estimated.
Right. Because you're either using the edge relation or the identity relation. You have nothing else, at least in this formulation. Okay. So, you have a graph G, and then you look at the power G to the K. And now I'm thinking abstractly for a minute, so I'm not specifying which. I mean, there's more products you can define. So, it's sometimes very interesting to understand what can you say about some graph parameter like maximal independence set in G, and how it looks when you look at the maximal independence set in G to the K. Okay? And this is something that I also care about from a theoretical computer science perspective, because, these are hard problems, like it's maximal independence is hard. And if I want to understand how hard it is, one tool that I have in my toolkit is taking this product and hoping that there will be some kind of hardness amplification. So as I said in the beginning of the talk, we're very successful in hardness amplification because we can do all these kind of operations like taking product, and often we are able to prove that the hardness gets amplified. Okay, so one kind of a question to look at is, if you have some graph such that independence set is hard to approximate on this graph to within some factor, could it be that on the power graph the independence set is hard to approximate to within a larger factor? Okay, so this is the amplification. There is some measure of hardness or complexity. In this case, I'm saying the hardness of approximation factor. But if this doesn't mean quite something concrete to you, just think of it as some measure of complexity. Okay? And then you want to say that you start with something that's mildly hard, you do a natural combinatorial operation, and you end up with something that's harder. Okay, so this is the broad context where these things are interesting. If you've not heard these things before, in complexity there's many other scenarios where you do this kind of operation when you care about various complexity measures. Communication complexity, circuit complexity, average hardness, approximation hardness. So there's many different areas where you have some measure of complexity. It's very hard to prove not unconditional lower bound on it, but you can show that if you have something that's a little bit hard, then you can do this kind of combinatorial reductions and get something that's harder. So we have a lot of this kind of results that say, you know, if there is a function that has no circuit that approximated better than 99%, then actually there's another function that no circuit can approximate it to within 51%. So kind of the hardness got amplified from just 1% hardness to 49%. Okay, so here I'm kind of thinking of amplifying some kind of hardness for independent set by moving from G to G to the K. So before I dive into it, I want to relate this to the previous section in my talk. So you see that what is this G to the K? The vertices are V to the K, right? And the edges are whatever combiner function I choose. So, you know, if my goal is to prove hardness amplification, I get to choose the function in the way that is best for me. You know, but there's only a fixed number of ways. Okay, so now, you know, each vertex here is a k-tuple of vertices. So if I think of the vertices V as numbered from 1 to n, then each vertex here, you know, is this I1 to Ik that I had before. It's just a k-tuple of old vertices. And now when I think about the maximal independence set in this graph, and I want to argue about it, say I want to show that, you know, if the independence set here was not too large, then the independence set here is also not too large. Okay, then when I argue about this independence set, what I have at my disposal is like I have this k-tuple, and it has edges to other k-tuples according to this relation. Okay, so I think of it like in the direct product scenario. These are like the other people that this k-tuple is talking to. Okay, this k-tuple is only kind of, you know, you want to decide if it's in the independence set or not, and the only people that affect this decision is the other k-tuples around it. So in some sense, you know, an algorithm solving any kind of problem like independence set or any other vertex cover, max cut in this graph, in some sense it's making a bunch of local decisions that depend on this kind of k-tuple local graph that was defined by G. And so somehow the combinatorics of this question are not very far from the combinatorics of the direct product question. And even more than that, I feel sometimes that the direct product question, since it doesn't have any extra structure, since here we have this graph structure that's unknown, it's a bit harder to get our hands on, the direct product question, a priori, there is no structure, it's just a string. So, you know, a string, it's a simpler object than a graph. Then it's kind of, it's easier to, you know, to argue there than it is to argue on graph. Okay, anyway, so the kind of questions that we ask are this. So let's focus on this, the tensor graph product. The reason I call it the tensor is because some people call it the weak graph product, some people call it the strong graph product. So, you know, if you think of the adjacency matrix of the graph G1 and the adjacency matrix of the graph G2, then the adjacency matrix of G1 times G2 is exactly the tensor of these matrices. Because you will have an edge in the product only if there's an edge here and here. Okay, so it's the tensor. It's a very natural, also kind of linear algebra works well with this, and eigenvectors and so on. Okay, so, okay, I don't know what's actually. Yeah. Okay, so let me just make 2 points and move on. So, you know, if the maximal click in G1 is something, so I know it's this size, and the same I know for G2. I write click, I mean the maximal click. Then, you know, it turns out then I know the maximal click of G1 times G2. Okay, and this is very easy times. And, you know, this is such a simple statement, it's also very easy to prove. Yeah, okay. On the other hand, if you look at some other parameter like the max cut or even the independent set, which looks very similar to click, this is the tensor. Sorry?
If I take again just h times, right? But now in this tensor product,
Yeah,
the result will be
two independent edges, right?
The peak number of that is still 2, not 2 times.
Why 2? It's 1.
Peak number of the first, peak number of h is 2, peak number of h is 2, but 2 times 2 is 4, not 2. Like in the second one it will 4.
It's something like maximum of the product.
You're right, but that's not... Okay, you're right, I'm sorry.
Still easy, but
It's still easy, but wrong. So I apologize. Okay, good. All right. So in this definition, the maximal click is right. As you said before, in this definition, the product of two edges looks like this, and then the maximal click became from 2, it became 4. So okay. So I guess this example, it's not for the tensor, it's for the Shannon product, like this. Okay? Yeah, okay, now I remember why it was here like that. Because then it leads you to ask, what about the independent set? So, okay, let's focus on this product where you allow a vertex to be either identical or to have an edge. Okay? So now you ask the same question about the independent set.
oh, but still there's something strange. Because if the big number is bigger than 2, it's not a product.
Let's, since for me personally, I can't think when I'm on stage, so let's put it offline. Okay, so now let's move to, this was only meant as an example to show how simple it is. Okay. Kind of leading up to the more difficult question, think of the same Shannon product, and suppose you know that the independent set is something, I don't know, M1, and you know that the independent set of G2 is M2. When I say independent set, I mean the maximal independent set. Now you want to know what is the maximal independent set of the product. And this is a very famous open question. Even for simple graphs like C7, we don't know. Okay, people think they know the answer, but we don't know how to prove it.
But you don't expect the formula, you expect bounds, is that right? It depends on G1.
No, that's a great question. So a priori, you might expect a formula, but then when you think about it, these questions are, you can even prove that they're computationally hard. So you cannot expect a formula for them, because what does it mean to have a formula? Well, the formula can be not interesting, like it equals itself, okay? But if you want a formula that is meaningful, it means you have some concrete way to compute it. But if this problem is computationally hard or undecidable or whatnot, you don't expect a formula.
But I'm saying, not in the sense of computation, it's not f of M1, M2, it depends on the graph.
On the graph. Right, so sometimes all you can hope for are bounds that relate to M1, M2, but you can demonstrate different graphs that have the same M1, M2, but different behavior later on. Yeah, so this is also...
For context, just to follow up on what you said,
Okay.
computing the limit of alpha is in the of
Yeah.
C5 to a high power was a major achievement of Lovaas. This is where he introduced the Lovaas theta function and so on. Just even C5 in the limit
Right,
was
right.
quite a major achievement.
Yeah, right. So, so for C5, it turned out to be computable. I mean, it's some kind of semi-definite program, but computing the theta function. For C7, it's already not known. All right, so moving on from this, next week, what I wanted to talk about, so I think Ehud might talk a little bit about independent sets in graph powers, and I might talk also about that a little bit and about what we know about max cut in graph powers and so on. So this is a topic we might touch. Now, last topic I want to talk about is products of games. So just before I say what a game is, see, I wrote here the word CSP, constraint satisfaction problem. Kind of from a theoretical computer science perspective, moving from graphs to CSPs is very natural. So a CSP is just, you have a collection of variables with some relations on them, like a kind of a hypergraph, or even a graph if it's a binary CSP. And then you're allowed to give values to these variables. And each constraint tells you which pairs of values are legal. Okay, so then you can ask, okay, I want to think about taking products of CSPs. So I have some three-set formula. That's an example of a CSP. What does it mean to take, the product or the power of this CSP? Is there an analogous way to do it, just like you do it for graphs? And as I showed here, for graphs, there's more than one way to define it. You can imagine that also for CSPs, there's analogous several ways to define the product of CSPs. And this is not that well studied at this point. But we have some results. Kind of the buzzword here is parallel repetition. And so now I want to talk about that a little bit. So instead of kind of defining CSPs and so on, one way to think of CSPs is through games. So let me define a two-player game. Okay, so we have two players. So one of them is traditionally called Alice, and the other is called Bob. And there is a referee. Okay, and the referee has a distribution over question pairs. So you can think of it as like a bipartite graph, where, for every pair of, so there's all the Alice questions, there's all the Bob questions, and an edge is a pair of questions. Okay, so the referee, let me also draw that here. So I have here all possible questions for Alice. These are just numbers from 1 to n. And these are the questions for Bob. And then, there's a weighted graph on here. And let's even assume that it's a probability over weight. So there's a probability distribution here over pairs. The referee chooses an edge from this distribution and sends the questions to Alice and Bob. So the referee sends U to Alice and V to Bob. Okay. And then Alice and Bob, they have a wall between them. They cannot talk. They can talk ahead of time, but then once they get the questions, Alice's answer cannot depend on V. It only depends on U. She can toss coins if she wants. You can show that it doesn't help her. So the referee sends her a question, and she needs to give back an answer. And similarly, Bob needs to give back an answer B. Okay, and then when the referee chose this edge, he also, along with this edge, he chose what we call a constraint, pi uv, which is basically just a collection of pairs of answers that would cause the referee to accept. So when he sees A and B, he checks if this was one of the pairs of labels that are good, and then he says if he accepts or not. Accept or reject. Okay, so this is a game. Okay, so just kind of to say again, you can think of the game in this way, or you can think of it as what we call a label cover instance, where it's a bipartite graph. Every edge comes together with a constraint, and there's some underlying alphabet from which the answers of Alice and Bob come from. Okay, so maybe they answer with bits, maybe they answer numbers from 1 to 10. There's some alphabet. Everything is finite. Okay, so this is called the label cover instance. And the question we're interested in this kind of game or label cover is, what is given a specification of a game, meaning you see the graph, you see the constraints, what are the best strategies for Alice and Bob? How well can they succeed in this game? Okay, so this is called the value of the game. The value, best success over all strategies. Okay, and just to say, in in the model, it's allowed that Alice will use randomness to give her answer. But you can show that it's not going to help her. If there's a randomized strategy, there's also a deterministic strategy. Because, assuming Bob already fixed his strategy, then for every question for Alice, there's a best response that she can answer, and it's deterministic. There's no need to choose between more than one best event. So she can be deterministic, and then also when you fix Alice, Bob is symmetric, so their strategies are deterministic. So it means that Alice can really answer according to a strategy from the questions U to the alphabet, and Bob can answer from the questions V to the alphabet. Okay, so this is the game. Now, what does that have to do with CSPs? So an example, let's think of an example of a game. A three-set game. So, מצבי טוב? Okay. So, everyone knows what three-set is?
Take a minute and see.
I can assume it. Okay, good.
No. Take a minute and say.
Take a minute and say. מה אתה? Yes. Okay, three-set game. Okay, so take a minute and say. So, three-set, so let me say what three-set is. So, three-set is a computational problem. You have variables x1 up to xn, Boolean variables, sorry, and you have clauses, C1 up to Cm are clauses. So what are clauses? A clause is something like this: xi or xj or not xk. So it's an OR of three literals. A literal is either a variable or its negation. It's a CNF. Okay, so CNF. So a three-set is called satisfiable if there is an assignment to the variables such that every single clause is satisfied. Okay, so goal, find assignment to variables satisfying all clauses. This is the goal in this specific problem. So if you like to think of graphs and hypergraphs, this is like a three uniform hypergraph whose vertices are, well, they're either the variables or the literals, depending how you like to think of it. So concretely, this is a good definition. You have a collection of clauses. Each clause is a three-tuple of literals. All right, and your goal is to satisfy all the clauses, and this is known to be NP complete, meaning it's among the problems whose solution you can check. This is the hardest. There are many other problems who are also the hardest, but if ever there is a polynomial time algorithm found for this problem, then there is a polynomial time algorithm for all of NP. And so this is a very basic question that we like in computer science, because on one hand, it's very simple and very local. Each constraint only looks at 3 bits. It's very local. And on the other hand, it captures all of NP. So it captures all of the computations that are in NP, which is a very broad class. Okay, so this is three-set. Now, what is the three-set game? The three-set game is a game where Alice is asked a clause and Bob is asked a variable. So, in clause versus variable game, three-set. By the way, the 3 from three-set is because each clause depends on 3 literals. There's also k-set where each clause depends on k literals. Okay, so what is this game? it's an Alice-Bob game where the referee acts as follows. The referee sees a three-set formula, all of them see it. And then the referee chooses one of the clauses at random, from 1 to m, and he tells Alice the entire clause. He tells her, I chose the clause xi or xj or not xk. And then he also chooses one of the three literals at random, the first, the second, or the third, and he sends to Bob, say he chose this one, he sends to Bob xk. Okay? So Alice gets to see the entire clause, and Bob just gets to see one of the three variables participating in the clause. So Alice gets a clause, and Bob gets a variable. And then they each respond. Alice should say, okay, you gave me this clause. The variables, the value of the variables in this clause are, 1, 0, 0. She needs to give some value that satisfies the clause. Okay? The goal of Alice and Bob are to convince the referee that the formula is satisfiable. And the referee wants to make sure that that's true. He doesn't want to be convinced if that's not the case. Okay, so Alice needs to give a satisfying assignment to the clause, and Bob needs to give a value to the variable that he got. So Bob only gets to see xk, and the point is that he doesn't know if xk came from this clause or from maybe some other clause that involves xk. Because that's the difficulty of the game. Okay, so the referee accepts if values are both consistent and satisfying. So satisfying means that Alice's answers satisfy the clause, and consistent means that Bob's answer is consistent with Alice's answer. So now the claim is that the Alice and Bob have a winning strategy So you see that Alice and Bob are cooperating. They win together. Okay, so they're not playing against each other. They're really playing against the referee. Okay, they want the referee to always accept. Okay, so they have a winning strategy if and only if the reset formula is satisfiable. Okay, so one direction is easy. If there is a satisfiable assignment, then Bob will always answer according to that assignment. Alice will always answer according to that assignment, and they'll always win. What if there is no satisfying assignment? Then, Bob will answer according to something, so his strategy is really some kind of assignment to the variables. And since I just said, suppose there is no satisfying assignment, it means that his strategy will violate at least one clause. Okay, and then Alice is stuck with, so they talk ahead of time, so they coordinate, and Bob tells Alice, look, I'm going to use this strategy. So Alice already knows which clauses of hers are going to be problematic, and she can maybe change the answer on these clauses and say something else. But, whatever she does, so if some clause was not satisfied by Bob's assignment, then there's nothing she can do. Whatever she says will be inconsistent with one of the variables. And if it so happens that the referee asked her that specific clause, then of the three literals that she has, at least one of them is inconsistent with Bob's answer. And so they will, on that specific pair of questions, they will fail. Okay, so this proves this claim. So what this means is that since 3-set is NP-hard, it means that deciding the value is the best success probability of all strategies. So deciding this value for a given game is an NP-hard question. In fact, deciding if the value is 1 or not is NP-hard. Okay? Yeah. To all three variables. To all three variables, yeah. Okay. So now, just like I was talking about with the robustness in the direct product, you might ask, Excuse me. You might ask about robustness of this question. You know, how hard is it to decide if the value of a given game is 1 versus the value of a given game is less than 1 minus epsilon. So what follows from the claim below is that deciding if the value is 1 or not 1, if I wrote here not 1, then we know that this is NP hard. We already know. So now what I want is a kind of hardness amplification. This is an easier task, right? You just need to say if it's 1 or 0.99 and below. So it's an easier task. And hardness amplification is a reduction from this task to that task, showing that, you know, if the first thing is hard, which we assume because we assume that P is not equal to NP, then we can prove that this thing is hard. And, you know, this is outcome of the PCP theorem. So PCP stands for probabilistically checkable proofs. It's a theorem that, let me say it one way, it's NP hard to decide if a given three-set formula has value 1 or at most 1 minus epsilon for some fixed epsilon. Okay, so this is the PCP theorem. The reason it's called the PCP theorem is because there is this interpretation of a probabilistically checkable proof. So this is a proof. One proof for the fact that a formula is satisfiable is to just give the assignment to the variables. And then you can just plug it into the clauses and you'll see if the proof is correct, you will be convinced in linear time. However, in probabilistically checkable proofs, you don't want to spend linear time reading the entire proof. Instead, the verifier has randomness and tosses random bits and then just chooses constant number of locations in the proof. Okay? And the PCP theorem says that even such a weak verifier that only looks at a random constant number of bits or 3 bits will catch a false proof with some constant probability. So here the probability is epsilon, right? Because with there is a way to convert this statement to a probabilistic verifier. I won't do it now. Okay, so this is a PCP theorem, and so now there's an even stronger version of this, which I call the strong PCP theorem, in which now I'm not going to talk about a three-set formula anymore. I'm going to go back to talking about games. Okay, just to clarify, this theorem, together with this reduction that I showed while stating this claim, can be rephrased to say it's NP hard to decide if the value of a given game is 1 or at most 1 minus epsilon, right? Because I just, I already know this theorem, so I look at the three-set formula and I look at the corresponding game, the clause versus variable game, and if this formula had value 1, there's a perfect strategy. And if the value was no more than 1 minus epsilon, you can prove that the best strategy will achieve at most 1 minus epsilon over 3. You just follow the kind of argument that we did, and you'll wind up with a gap between 1 and 1 minus epsilon over 3. Okay? So the PCP theorem really implies that this is NP hard. It's not how hard, it's NP hard. Okay? So the PCP theorem implies that it's hard to decide if the value of a game is 1 or at most 1 minus epsilon. And kind of, this is a gap amplification idea, right? You start from hardness between 1 and not 1, and you amplify the gap between them to 1 and 1 minus epsilon. But the proofs kind of are rather involved and take many steps. However, to move from this theorem to this theorem, it's just by direct product. So let me state what the theorem is. It is NP hard to decide if a given game has value of the game 1, or the value of the game is at most epsilon. And now the quantifier is that for every epsilon. Okay, so the gap suddenly grew to, it's not between 1 and 0.99, it's between 1 and 0.01. Okay, so for any constant epsilon, this is hard. And to prove this theorem from this theorem, okay, so, you know, the reason we care about this theorem is that it has a lot of applications. I won't talk about it now, but the fact that the gap is large is very, very useful, because it shows really that you can almost model it like Alice and Bob have zero, you know, epsilon coordination between them. Like, no matter how they plan ahead of time their strategies, you know, on a random edge, it will look like they're completely answering independent answers. There's almost no correlation between them, only epsilon. And once you have that this problem is hard, you can use it to reduce from it to a lot of CSPs and a lot of stuff. So anyway, how do you prove this from this? The answer is you just take the direct product of the game. So let me end this talk by defining what is the direct product of the game. Something we call parallel repetition. Then next week, I will prove part of this theorem. Okay, so the direct product of a game, it's best to think of it in this setting. So the game is given by this level cover instance, but to think about parallel repetition, it's good to think of it here. So I can define the direct product of two different games, but let's think even of defining the direct product of G with itself. So now, instead of the referee choosing a random edge, the referee chooses two random edges independently. Okay, so the referee chooses U1, V1, and then he also chooses U2, V2. Okay, and remember that with each edge, okay, so this is U1, V1, and this is U2, V2, and with each edge, there's also a constraint. And then the referee sends all the U questions to Alice. So this goes to Alice. And he sends all the V questions to Bob. Okay, and then Alice comes back with two answers, A1 and A2. So this is her answer. It's a concatenation of two answers. And this is Bob's answer, B1 and B2. Okay, and then what does the referee do? He checks that A1 and B1 satisfied the first constraint, and A2 and B2 satisfied the second constraint. So accept. So the referee accepts if A1, B1 satisfy the first constraint, and A2, B2 satisfy the second constraint. Okay, so this is, now I've defined the game. And you can see already that, let's think of various aspects of the game. So the game is defined by a graph. The product of two games is really defined by the product of this graph with itself. And this is the tensor product, right? Because I put an edge between U1, V1, and between U1, U2 and V1, V2, if there was an edge in every coordinate. So here there's only two, but there could have been K. Okay, so the graph structure is just the product structure. And then the answers, instead of answering just one answer, A1, or one answer, A2, Alice needs to answer for every coordinate. So the answers are concatenation, like in the direct product that we started with, where you're asked I1 up to IK, and you need to give an answer for each coordinate. So it's the same. And the tests test that each of the coordinates satisfy the corresponding constraint. Okay, so this is the definition of the direct product of games, we also call it parallel repetition. And now let me, great. So now you can ask, just like I slightly unsuccessfully was trying to convince you with click and independent set that, sometimes this question is easy and sometimes it's hard. You can ask, given value of, suppose you know something about the value of G1 and you know something about the value of G2, can you deduce something about the value of G1 cross G2? Right, and like Ron said, this can be a very complicated structure. So it's not like you expect there to be an exact formula. It's more like bound. Suppose you know a bound about value of G1 and G2. I'm interested in finding a bound about the value of G1 times G2. And a slightly simpler question is, if I know that the value of G is bounded away from 1, like this, for example, like I have here, that the three-set game here, it's hard to decide if it has value 1 or 1 minus epsilon. And now I'm thinking about the game obtained by parallel repeating this k times. Okay, so maybe I should have said before, if you take a game with value 1 and you do this parallel repetition, it's obvious that the value remains 1, right? Because Alice and Bob can just use the same strategy on each coordinate. The question is, what can they do if their value of their initial game was 1 minus epsilon? What happens if I do a parallel repetition and I ask k tuple of questions? What can they do? Okay? And so this was this question has a famous history, and initially it was believed that it was obvious that the value decays like 1 minus epsilon to the k, but this is famously not true. And let me give you a nice example, but to end. But just to say that although this is not true, we know that the behavior does go exponentially to 0 with k, and this is the famous parallel repetition theorem proved by Ran Raz in '95, and we'll talk about it more next week. So let me finish with this nice example due to Uri Feige that I really like. So think of this simple game. We have Alice and Bob, and the game is this. Alice tosses a random coin, unbiased coin, and Bob needs to guess what the value is. Okay? So that's one game. What is the best strategy for this game? What is the value of this game? Thank you. So it's half. Now we have this other game. Bob tosses a random coin, and Alice needs to guess the value. Who can tell me what? Okay, so that's all half. Yeah, you can think about it. There's whiteboards outside. You can figure it out. So now, what is the parallel game? Well, both of them privately toss their own little coin independently, and each needs to guess the value of the other. Okay, so naively, the value of this game is a quarter, but there's maybe more things that they can do. So I leave it for the break. Okay.